Hello, and welcome, weary traveler, to Sleepy Wiki. Find a comfortable space, let your shoulders gently drop, and allow your breath to slow, becoming soft and deep. Tonight, we drift to the very edges of our solar system, far beyond the familiar orbits of planets, past the Kuiper Belt, into a realm of profound quiet and unimaginable cold. We'll speak of a vast, spherical shell of icy bodies, a cosmic archive holding remnants from the very dawn of our sun. Imagine a deep, dark reservoir of ancient ice, where countless dormant comets patiently await their turn to awaken and journey inward. It's a place where time moves slowly, almost imperceptibly, a silent guardian at the frontiers of the known. We'll explore this distant, ethereal boundary, not with urgency, but with the gentle curiosity of a nighttime wanderer. If these quiet journeys through knowledge bring you comfort, you might consider a gentle tap on the like button, or perhaps subscribing, to help more sleepy minds find their way here. Now let us begin our soft descent into the dark, silent majesty of the Oort Cloud. But how did this magnificent, ethereal boundary come to be? How did these countless frozen whispers of the early solar system find themselves in such a distant, delicate embrace? To understand the Oort Cloud's formation, we must rewind the cosmic clock, not just by a few centuries or millennia, but by billions of years, back to the very genesis of our solar system, roughly 4.6 billion years ago. Imagine, if you will, our young sun, not yet the serene beacon it is today, but a new star, glowing fiercely within a swirling disk of gas and dust, a vast protoplanetary nebula. This was a cosmic nursery, bustling with creation, a grand stage where planets were beginning their long, slow dance from the primordial fog. Within this disk, far from the sun's scorching warmth, in the colder outer regions beyond what astronomers call the frost line, countless smaller icy bodies were coalescing. These were the planetismals, the very building blocks of planets, small icy pebbles and rocks, pristine and untouched, composed of frozen water, methane, ammonia, carbon dioxide, and carbon monoxide, much like the ingredients for comets we know today. Initially, these icy seeds moved in relatively stable circular paths, patiently orbiting our fledgling sun. But this calm was not to last. In the heart of this cosmic ballet, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were rapidly growing, accreting vast amounts of gas and dust, quickly swelling to their immense sizes. As they grew, their gravitational influence became incredibly powerful, akin to giant, invisible hands stirring the cosmic pot. This is where the story of the Oort Cloud truly begins, with a powerful, chaotic dance of gravitational interactions. Picture these newly massive giant planets, especially Jupiter and Saturn, like colossal celestial slingshots. As they migrated slightly in their early orbits and swept through the vast population of these icy planetismals, they exerted an immense gravitational pull. Many of these icy bodies, once on stable paths, were no match for the might of these nascent giants. Some were drawn into collisions, swallowed whole by the growing planets. Others were ejected outwards, not gently, but with powerful, sweeping gravitational kicks. Each close encounter was a silent, powerful whisper, a gravitational nudge that propelled these tiny worlds further and further from the sun's strong central embrace, It was a grand game of cosmic billiards played on an unimaginable scale. These initial interactions flung the icy bodies in every conceivable direction. Some were even ejected completely from the solar system, lost to the cold void of interstellar space forever. But a significant number, those that received just the right amount of gravitational energy, embarked on an extraordinary journey. They were propelled into extremely elongated, elliptical orbits, reaching incredible distances from the Sun. Think of them like dandelion seeds caught on a powerful gust of wind, drifting outward into the deeper darkness, their trajectories forever altered by the gravitational breath of the giant planets. As these icy wanderers sailed into the profound depths of space, a second, more subtle set of forces came into play, crucial for shaping them into the spherical Oort Cloud we envision today. Our Sun, in its infancy, was not alone. It was born in a bustling stellar nursery, a densely packed cluster of thousands of other young stars. As these stars drifted past our nascent solar system, their collective gravitational fields provided gentle yet persistent nudges. These distant stellar encounters acted like a kind of cosmic stirring, slowly but surely modifying the highly eccentric, elongated orbits of the flung-out, icy bodies. Over millions of years, these external gravitational influences began to circularize their paths, making them more stable and decoupling their orbits from the plane of the planets. It's like a soft, overarching hand gently smoothing out the rough edges of their initial chaotic flight, guiding them into more stable, yet highly inclined and broadly distributed paths. Even after our Sun drifted away from its birth cluster, a much vaster, more enduring force continues to exert its subtle influence, the galactic tide. The sheer, colossal mass of our Milky Way galaxy, with its spiral arms and central bulge, creates a gentle, omnipresent gravitational field that subtly tugs at everything within it. This galactic tide, a barely perceptible differential gravitational force across the immense span of the Oort Cloud, further helps to shape its spherical distribution and maintain the nearly random inclinations of its icy inhabitants. It's like a colossal invisible current in the ocean of space, gently guiding these distant objects into their grand, encompassing shell around our Sun. So, the Oort Cloud, then, is not merely a collection of icy rocks. It is a grand, frozen archive of our solar system's tumultuous youth. It is composed overwhelmingly of those very same icy planetismals that formed in the outer protoplanetary disk, flung outward by the gravitational might of the growing giant planets, and then gently herded into their vast, spherical reservoir by the gravitational whispers of neighboring stars and the enduring embrace of our galaxy itself. This theory elegantly explains why the Oort Cloud is so spherical, why its objects have such random orbital inclinations, and why they are predominantly made of the pristine, volatile ices that condensed far from the Sun's early heat. While the ejection of planetismals by giant planets is the overwhelmingly dominant theory, astronomers also consider the possibility that a small fraction of the Oort Cloud's inhabitants might have been captured from other star systems during the Sun's early, close encounters with its stellar siblings. These interstellar interlopers, if they exist, would add another layer of fascinating complexity to this distant realm, perhaps even hinting at the diverse building blocks of other planetary systems. But for now, we understand the Oort Cloud largely as our own solar system's scattering field, a vast, cold museum of its tumultuous beginnings. These tiny icy worlds, now residing in the tranquil deep freeze far beyond our comprehension, are like time capsules, perfectly preserved remnants of the ingredients from which our planets were made. They hold within them the original chemistry of the solar nebula, offering us silent clues about the conditions of creation. But what exactly are these ancient, icy travelers made of? And what stories do their frozen hearts truly hold about the dawn of our solar system? Perhaps we can gently explore that mystery next. Tonight, let us venture deeper into its structure to understand how this colossal reservoir of potential comets is organized, much like a magnificent celestial onion, with layers that tell tales of its formation and its profound connection to the wider galaxy. Imagine, if you will, a vast, gentle embrace around our sun, far beyond the furthest planets, yet still somewhat tucked in. This is the inner Oort Cloud, sometimes whispered about as the Hills Cloud, named after the astronomer Jack Hills, who first theorized its profound importance. It begins, roughly, at a distance of about 2,000 astronomical units from our Sun. That's 2,000 times the average distance from our bustling Earth to our familiar, life-giving Sun. To truly grasp this immense scale, consider that Neptune, our outermost giant, a planet that already feels so incredibly far away, is only about 30 AU from the Sun. So when we talk about 2,000 AU, we are truly sailing into the profound, silent deep, where the sun's light is a distant gleam, and its warmth utterly absent. This inner region then stretches out to a staggering 20,000 astronomical units, an expanse so vast it's almost beyond our everyday comprehension, yet quite compact, a relatively dense core when compared to the truly expansive grandeur of its outer counterpart. Think of it as the denser, cozier heart of the Oort Cloud. If the entire Oort Cloud were a sleepy, sprawling nebula, the inner part would be its calm, protected core, a bit like the tightly packed heartwood of an ancient tree, strong and resilient. Its shape isn't perfectly spherical, but more like a very thick, somewhat flattened disc or a donut, a toroid. Imagine a donut whose hole has almost closed up, leaving a thick, rounded ring. This shape is a whisper of its tumultuous past, a memory of the material that was once scattered by the gravitational dance of the giant planets in the early solar system, Jupiter, Saturn, Uranus, and Neptune, all playing their colossal roles, flinging icy debris both inward and outward, eventually nudged and pulled into this somewhat flattened configuration, a cosmic memory preserved in ice. But here, the icy bodies are much more concentrated. While still incredibly sparse by earthly standards, you wouldn't be bumping into them every day. They are packed perhaps 10 to 100 times more densely than in the outer regions. It's a vast cosmic nursery, holding billions, perhaps even trillions, of icy worldlets, the primordial building blocks of our solar system, preserved in deep freeze, untouched for billions of years. These aren't just little snowballs. They can be kilometers across, veritable mountains of ice and dust, dormant and patient, holding within them the pristine, unaltered chemistry of the very dawn of our stellar neighborhood. The inner Oort cloud is also more strongly bound by the sun's gravity. It feels the sun's magnetic pull more directly, more intimately. This closer proximity offers it a measure of protection, a comforting gravitational anchor. It's less affected by the gentle tugs and pushes from the Milky Way galaxy, less perturbed by the occasional passing star that might drift by on its own cosmic journey. It's like a child holding firmly onto a parent's hand in a bustling market. While the market swirls around, the child remains secure. This stability is incredibly important, for this inner region acts as a kind of long-term comet reservoir, a deep freeze bank account of icy wealth. When the outer Oort cloud loses some of its icy residence to the inner solar system, the inner cloud can gently replenish it, a slow, majestic cosmic exchange over billions of years, ensuring a continuous supply of potential comets, like a patient artisan slowly carving new treasures. Now, let us float further out, beyond this protected core, into the truly immense, almost boundless expanse of the outer Oort cloud. This is where the Oort cloud truly earns its reputation as the most distant realm of our solar system, stretching from that 20,000 AU mark all the way out to an astonishing 100,000 AU, or even sometimes estimated to be as far as 200,000 AU. To give you a true sense of this distance, 100,000 AU is roughly 1.5 light years. Yes, you heard that right. We are talking about distances measured in light years, almost halfway to the nearest star system, Proxima Centauri. Our sun, from this unimaginable vantage point, would be but a bright, distant star among countless others, barely distinguishable from the starry tapestry of the Milky Way. Unlike the inner cloud's somewhat flattened form, the outer Oort cloud truly is a vast, ethereal sphere. A magnificent, ghostly bubble encircling our entire solar system. Imagine a giant gossamer sphere, almost perfectly round, enveloping everything we know, its sheer scale mind-boggling, a testament to the colossal yet diminishing reach of our sun's gravitational influence. It is here that our solar system truly begins to blend into the interstellar medium, where the sun's domain gradually gives way to the broader galaxy. But within this immense volume, the icy bodies are spread incredibly thin. This region is far sparser than the inner cloud. If the inner cloud was a bustling city park, the outer cloud is like a vast, untouched wilderness where individual trees, or in this case, icy worldlets, are separated by immense, silent distances. A passing space traveler might journey for centuries without encountering a single one, even though trillions are thought to reside here, each a lonely sentinel in the cold, dark void. They are truly the lost sheep of our solar system, drifting in splendid isolation, waiting for a whisper of change. And it is here, in this fragile, far-flung dominion, that the dance of the long-period comets truly begins. The outer Oort cloud is barely held by the sun's gravity. Its icy inhabitants are like leaves gently clinging to the very edge of a branch, susceptible to the slightest breeze. And those breezes come in the form of cosmic influences, the galactic tide, from the sheer immense mass of the Milky Way galaxy, gently tugging at them like an invisible hand slowly stirring the celestial pot. The gravitational whispers of passing stars. As they wander through our cosmic neighborhood, their own gravity creating ripples that can dislodge an icy worldlet, or even the subtle disturbances from massive molecular clouds that occasionally sweep through our solar system's distant periphery, their density enough to exert a gentle yet profound nudge. These external nudges, these cosmic whispers, are enough to dislodge an icy body from its ancient, sleepy orbit. When that happens, when one of these icy slumberers is nudged just so, it begins a slow, inexorable tumble inward, a journey of hundreds of thousands or even millions of years, eventually manifesting as a spectacular long-period comet streaking across our night sky, a messenger from the very edge of forever, a relic from the dawn of time, bringing with it secrets from the deep freeze of space. The outer cloud, being so tenuous and exposed, is constantly losing its members, like sand grains slowly slipping through an hourglass. Over billions of years, it would have been depleted if not for the denser, more resilient inner Oort Cloud, which acts as its long-term stable supplier, like a patient artisan slowly carving new treasures to replenish the outer market. This intricate interplay between the inner and outer regions ensures the Oort Cloud's enduring presence, a deep freeze archive of the primordial solar system. So we see the Oort Cloud not as a uniform sphere, but as a structure with distinct regions, each playing a crucial role in the grand cosmic ballet. The dense, toroidal inner Oort Cloud, a protected heart, acting as a stable reservoir, and the vast spherical outer Oort Cloud, sparse and vulnerable, yet the very source of those magnificent long-period comets that occasionally grace our skies. Each layer tells a story of creation, of gravity's reach, and of the subtle but powerful influences of the galaxy beyond. And as these icy bodies drift, held in this delicate balance, they hold within them clues not just about our solar system's birth, but about the very raw materials from which planets, and perhaps life itself, could arise. Next, we will gently explore the composition of these icy wanderers themselves, what hidden ingredients lie beneath their frosty exteriors as we continue our quiet journey through the Oort Cloud. So what are these countless tiny worlds truly made of? What ancient, slumbering secrets do they hold within their deep freeze? Imagine, if you will, a cosmic pantry, or perhaps a colossal freezer, stocked not with everyday groceries, but with the very pristine ingredients of creation itself, kept perfectly preserved in a deep, perpetual chill. The objects within the Oort Cloud are, at their heart, magnificent cosmic icebergs. But these aren't just any icebergs. They are ancient, dark, and utterly pristine, holding the very essence of our solar system's youth, locked away in an eternal deep sleep. At the core of their being, much like a familiar comfort, you'll find water ice. Yes, the same water that fills our oceans and forms the clouds above us, but here, in this distant realm, it exists in a state of suspended animation, locked in an eternal slumber for billions of years. Picture a tiny, rugged sphere, perhaps only a few kilometers across, tumbling silently through the cosmic void, a celestial pebble of forgotten time. Its surface, dark and unassuming, hides vast quantities of frozen water, not sparkling and crystalline like fresh snow, but often amorphous, like supercooled glass, a profound testament to the unimaginable cold of its birth. This water isn't just a simple block. It's a silent, frozen witness to the very moment our sun ignited, a time capsule of primordial H2O, holding within its structure the earliest memories of our cosmic home. But water is only the beginning of this celestial recipe. As we delve deeper into the Oort Cloud's cold embrace, we discover a symphony of other, equally fascinating ices, each holding its own unique story. Among them is methane ice, the same gas that forms the hazy, turquoise atmospheres of distant giant planets like Uranus and Neptune. Here, in the Oort Cloud, it's frozen solid, a quiet ghost of ancient atmospheres, perhaps whispering faint tales of the raw materials that built those colossal gas giants. Imagine these frozen methane deposits as tiny pockets of congealed whispers, patiently awaiting an awakening, preserving a cool, bluish tint of cosmic history. Then there's ammonia ice, a substance with a distinctive sharp scent when encountered on Earth. But in the Oort Cloud, it lies dormant and inert, a fundamental building block of organic chemistry, a silent promise of complexity. It gently reminds us that even in these sterile, profoundly distant realms, the fundamental ingredients for life, in their most basic forms, were present from the very beginning. These frozen ammonia crystals are like miniature prehistoric chemical laboratories, locked in a deep, timeless freeze, holding blueprints for future wonders. And the icy procession continues. We find carbon monoxide ice, and its slightly more complex cousin, carbon dioxide ice, what we know on Earth as dry ice. These are the frozen breaths of nascent stars and the raw material for colossal molecular clouds, locked away in solid form, perfectly still. Imagine them as tiny dark blocks of solidified exhalation from the universe's earliest moments, carrying with them the very carbon atoms essential for all known life, stored in quiet cosmic solitude. These frozen gases represent the abundant carbon and oxygen that pervade the cosmos, here captured in silent, solid form, utterly still and deep. Beyond these well-known volatiles, scientists also believe these objects harbor more exotic, intricate ices, such as hydrogen cyanide, HCN, and formaldehyde, H2CO, which are themselves complex organic molecules. These aren't just random components, they are precursors to amino acids and other fundamental biomolecules, gently suggesting that even the most distant frozen reaches of our solar system were seeded with the potential for life's intricate dance. Think of them as tiny, pre-programmed chemical packets, awaiting the right conditions to unfurl their intricate molecular structures, like sleeping code for the universe. While ice undeniably dominates, these Oort Cloud objects aren't purely made of frozen gases. Interspersed within this vast icy matrix are tiny flecks of rocky and dusty material. Silicate grains, much like the sand on a moonlit beach, but on a cosmic scale, mixed with darker, tar-like organic compounds often referred to as tholins. These are the gritty, solid remnants, the cosmic dust bunnies that didn't quite make it into a planet or an asteroid closer to the sun. They add texture and substance to these otherwise ethereal ice spheres, providing a dark, absorbing surface that helps them remain incredibly cold and hidden. Imagine them as scattered, microscopic pebbles and dark, sticky residues embedded within the ancient, patient frost. What truly makes these compositions extraordinary is their astonishingly primitive nature. These aren't materials that have been significantly altered by heat, pressure, or turbulent geological processes. They are, essentially, pristine samples of the protoplanetary disk from which our entire solar system was born some 4.6 billion years ago. Think of them as cosmic fossils, perfectly preserved specimens from a time before Earth, before Mars, before Jupiter even found its final magnificent form. They are the untouched, raw ingredients, a detailed chemical blueprint of our solar system's infancy, kept in the coldest, darkest, most silent vault imaginable, whispering tales of cosmic beginnings. They originated far closer to the Sun, within the inner regions of that colossal, swirling disk, but still beyond the crucial frost lines. Those critical distances from the young Sun where specific gases became cold enough to condense into solid ice. Water ice formed closer in, then methane, then carbon monoxide as temperatures plummeted further out into the nascent nebula. These tiny, icy planetesimals, laden with their diverse frozen cargo, were then gravitationally flung outwards by the mighty giant planets. Jupiter, Saturn, Uranus, Neptune, like countless pebbles scattered by a giant's gentle yet powerful hand. They were sent on a long, slow journey to the deep freeze of the Oort Cloud, where they have remained largely undisturbed in quiet contemplation ever since. How do we know all this, you might gently wonder, about objects so incredibly distant and dim? The answer lies in their occasional dramatic awakenings. When one of these Oort Cloud objects is softly nudged from its slumber by the gravitational stirrings of a passing star or molecular cloud, it begins a long, slow, graceful fall towards the inner solar system, transforming into what we know as a long-period comet. As it approaches the Sun, its ancient ices, undisturbed for eons, begin to warm and sublimate, turning directly from solid to gas. This process releases a spectacular glowing coma of gas and dust, and often forms a brilliant sweeping tail, allowing us to directly analyze the chemical signatures of these primordial ingredients from Earth-based telescopes and even advanced spacecraft. Each comet, therefore, is a silent messenger from the Oort Cloud, carrying with it tales of the solar system's birth, laid bare for us to read in its shimmering ethereal vapor. So when you gaze at a long-period comet streaking across the night sky, perhaps on a clear, dark evening, know that you are witnessing the ancient breath of the Oort Cloud, a frozen whisper from the dawn of our solar system, revealing its secrets in a silent, spectacular, and profound display. Each molecule, each minuscule grain of dust, tells a story of creation, of deep space, and of time immemorial, a lullaby whispered across the cosmos. And as we consider these profound compositions, these silent, icy witnesses to our solar system's beginning, perhaps you might begin to wonder about the overall shape and vastness of this immense, icy reservoir. Where do these countless frozen memories truly reside, and how do they gracefully orbit our distant, guiding sun in their timeless dance? These frozen memories don't simply float motionless in the void. Within this magnificent spherical shell of icy solitude, billions upon billions of icy fragments drift, remnants from the very dawn of our planetary home, preserved in a deep freeze for nearly 5 billion years. These aren't merely inert rocks. Each tiny, distant worldlet, no bigger than a mountain or a city, is a sleeping giant waiting for a cosmic whisper. For while the Oort Cloud feels incredibly remote, it is not truly isolated. It exists within the vast gravitational tapestry of our Milky Way galaxy, and it is here that the subtle dance of gravitational dynamics truly begins to unveil the mysterious origins of comets. At these unimaginable distances, the Sun's mighty gravitational embrace, while still present, is stretched incredibly thin. Think of it like a parent's hand holding a child's kite string. Close by, the pull is strong and direct. But if that kite string were to stretch for hundreds of billions of miles, the connection, while still there, becomes delicate, easily influenced by passing breezes. In the Oort Cloud, these breezes are the gravitational whispers of other celestial bodies. Almost one of the most profound influences comes from the occasional slow wanderings of a passing stars. Our Sun, with its own retinue of planets and the Oort Cloud, is not alone in its journey around the galactic center. Thousands upon thousands of other stars orbit alongside us, occasionally crossing paths, not in a catastrophic collision, but in a graceful, distant flyby. Imagine a serene lake, its surface perfectly still. Now, picture another boat, miles away, gliding silently past. Even at that distance, its wake, though faint, can send gentle ripples across the water, eventually reaching your own boat and causing it to bob slightly. Similarly, when another star, or even a smaller, darker celestial body like a brown dwarf, meanders through the outer fringes of the Oort Cloud, still light years away from our inner solar system, its own gravitational field acts as a colossal, invisible hand. This gravitational hand doesn't snatch objects away directly. Instead, it subtly tugs and pulls, gently disturbing the finely balanced, nearly circular orbits of those icy residents. Some of these Oort Cloud objects, nudged outwards, might be softly pushed entirely out of the Sun's gravitational grasp, becoming interstellar wanderers, lost to us forever in the cold, dark ocean between stars. But marvelously, others are nudged inwards. Picture a tiny billiard ball, barely moving on a vast, dark table. Suddenly, a minuscule, unseen vibration causes it to roll ever so slowly towards the table's distant center pocket. This inward nudge is the first, almost imperceptible step in a journey that will take tens of thousands, sometimes even millions of years. It's a journey from the deepest, coldest reaches of our solar system, initiated by the faintest of cosmic nudges. These stellar perturbations are not the only sculptors of the Oort Cloud's destiny. Another, even more pervasive force is at play, the galactic tides. Our entire solar system, with its planets and its Oort Cloud, is embedded within the colossal gravitational field of the Milky Way galaxy itself. We are orbiting the supermassive black hole at the galactic center, along with hundreds of billions of other stars. This galactic gravity doesn't just pull us as a whole, it exerts a differential force, a stretching or squeezing effect across vast distances. Think of it like this. If you have a very long, delicate string and you hold one end closer to a strong magnet than the other end, the closer end will feel a slightly stronger pull. This slight difference in pull can create a stretching force along the string. The Oort Cloud, being so incredibly vast, experiences this same tidal force from the galaxy. The side of the Oort Cloud closer to the galactic center feels a slightly stronger pull than the side further away. This constant, gentle, differential tug acts like an immense, invisible hand, kneading and reshaping the orbits of the Oort Cloud objects over eons. It's a slow, rhythmic stirring, like ocean currents silently influencing every particle within their embrace. These galactic tides don't typically send objects hurtling inwards on their own, but they are crucial for setting the stage. They can gradually distort and elongate the orbits of Oort Cloud residents, making them more eccentric, more stretched out. An object with an already elongated orbit becomes far more susceptible to that crucial inward nudge from a passing star. The galactic tides are like the background hum, the constant, gentle pressure that primes the Oort Cloud for its dramatic displays. So an icy worldlet, drifting for billions of years, is subtly nudged by a passing star, its orbit already primed by the relentless stretching of galactic tides. It begins its long, slow fall. At first, it's just a lonely chunk of frozen water, carbon dioxide, methane, and ammonia mixed with silicate dust. It's too far away to feel the sun's warmth, a mere specks of primordial material. But as it plunges deeper into the inner solar system, an incredible transformation begins. It crosses the frost line of the outer planets, then approaches the inner planets, and finally draws nearer to the sun's warm embrace. The once frigid temperatures begin to rise. The surface of the icy body, still miles across, can no longer hold its frozen grip. The volatile ices, those ingredients of the early solar system, don't melt like an ice cube in a glass. They sublimate. That means they turn directly from a solid into a gas, bypassing the liquid state entirely, like dry ice steaming in the air. This escaping gas, carrying with it tiny dust particles, forms a hazy, luminous envelope around the comet's nucleus, which we call the coma. As the comet continues its journey inward, closer to the sun, the solar wind, a stream of charged particles flowing outwards from our star, and the pressure of sunlight itself begin to push this gas and dust away from the comet's head. And there, against the black velvet of space, the comet's magnificent tails begin to unfurl. There are typically two distinct tails. The dust tail, often broad and yellowish, composed of tiny dust grains gently pushed away by sunlight. It often curves gracefully behind the comet, following its orbital path. Then there's the ion tail, a slender, often bluish stream of ionized gas pushed directly away from the sun by the powerful solar wind. This ion tail always points directly away from the sun, a true compass of solar activity, sometimes appearing as a luminous, ethereal streamer. These spectacular visitors are known as long-period comets. Their orbits are incredibly eccentric, meaning they are very elongated, almost like a stretched-out ellipse. They spend millennia, sometimes hundreds of thousands or even millions of years, traveling from the outer reaches of the Oort Cloud, swooping once around the sun, and then beginning their long, slow retreat back into the frozen depths from which they came. Some may return if their orbits haven't been too greatly disturbed by gravitational interactions with the gas giants like Jupiter or Saturn. Others may be ejected entirely or break apart, leaving behind only scattered dust. The journey of each comet is a testament to the subtle but immense power of gravitational dynamics. It's a cosmic ballet orchestrated over unimaginable scales of time and distance, where the faintest tug can initiate a monumental journey. Each passing star, each galactic tide plays its part in awakening these sleeping icy sentinels and sending them on their brief, dazzling pilgrimage to the inner solar system. And as these magnificent ice worlds make their grand entrance, they bring with them more than just a spectacular display. They carry ancient secrets, frozen memories from the very beginning of everything we know. But what exactly are these secrets? What can these icy travelers tell us about the earliest days of our solar system, and perhaps even about the origins of life itself? That, my dear listeners, is a tale for our next quiet moment together. We've seen how these icy wanderers begin their journey inward, but what forces exactly orchestrate this cosmic awakening? Even in this profound stillness, forces beyond our sun's immediate dominion are constantly at play, gently, relentlessly, shaping the destiny of these frozen wanderers. The first of these profound influences is a majestic, slow-motion sculptor, an invisible hand reaching across the vastness of space. The galactic tide. Picture our entire Milky Way galaxy, that shimmering, spiral city of hundreds of billions of stars, as an enormous, living entity. Our solar system, with its distant Oort Cloud, is but a tiny, delicate leaf on one of its grand, swirling branches. Just as the moon's gravity pulls on Earth's oceans, creating our familiar tides, the colossal, collective gravity of the entire Milky Way exerts a differential pull on our solar system, and most particularly on the far-flung, loosely bound inhabitants of the Oort Cloud. This isn't a uniform tug. It's a differential stretch. Imagine the Oort Cloud as a colossal, ethereal balloon, barely tethered to our sun. The side of this balloon closest to the bustling galactic center feels a slightly stronger gravitational embrace from the galaxy than the side furthest away. And the parts of the cloud that lie along the galactic plane, perpendicular to the disk, experience a slightly different stress than those above or below. It's like a cosmic breath, gently, subtly, yet perpetually, stretching and kneading this vast bubble of ice. Over millions of years, this imperceptible stretching exerts a tiny but crucial torque on the orbits of the Oort Cloud's inhabitants. These aren't sudden yanks, but rather the most patient of nudges, slowly, incrementally altering the delicate balance of a comet's long-established trajectory. A perfectly elliptical orbit, stable for billions of years, might slowly, oh so slowly, become just a little more elongated, a little less bound, pushed ever so slightly towards an inward spiral. It's a testament to the sheer scale of the galaxy that its collective diffuse mass can exert such a profound, pervasive influence over such immense distances. The galactic tide is always there, an omnipresent, invisible current in the cosmic ocean, patiently, persistently working to reshape the fringes of our solar system. It's a quiet, fundamental force that ensures the Oort Cloud is not an entirely static place, but rather a slow-motion, ever-shifting frontier, its icy residents constantly, subtly, being encouraged to change their sleepy ways. But the galaxy holds other, more dramatic surprises in store for our distant comets. Beyond the patient, continuous pull of the galactic tide, there are moments of more acute, localized disruption, moments when individual cosmic travelers pass close enough to our solar system to make their presence powerfully felt. These are the stellar perturbations, and they act like a sudden, sharp whisper in the otherwise silent, deep space slumber of the Oort Cloud. Imagine a star, perhaps even a large luminous sun like our own, on its own immense journey through the Milky Way. Every few million years or so, one of these celestial wanderers might pass through our cosmic neighborhood, not close enough for a collision, of course, but near enough for its own powerful gravitational field to reach out and touch the very edges of our Oort Cloud. As this star sweeps by, its gravity acts like a powerful unseen hand, reaching into that vast sphere of icy bodies, giving some of them a decisive gravitational kick. Unlike the gentle, prolonged stretching of the galactic tide, a stellar perturbation can be a much more abrupt and violent event for an individual comet. The closer and more massive the passing star, the stronger the kick it imparts. A comet that was once in a stable, quiet orbit, perhaps already loosened slightly by the galactic tide, might suddenly find its path dramatically altered, its velocity changed, its trajectory bent sharply inwards towards the inner solar system, or, conversely, ejected entirely from our sun's gravitational embrace, sent drifting into the vast, lonely, interstellar void. And it's not just individual stars that can cause these dramatic disturbances. Sometimes, a passing giant molecular cloud, an enormous, diffuse but incredibly massive cloud of gas and dust, can drift near our solar system. Despite their low density, their sheer size and mass mean they can exert a formidable gravitational influence, acting like a cosmic fog bank that can stir up the Oort Cloud with unexpected force, sending ripples of gravitational disruption through its icy population. These are rarer events, perhaps, but when they occur, their impact can be profound, unleashing a torrent of new comets towards the sun. So, the Oort Cloud is a stage where two magnificent, invisible forces constantly dance: the slow, pervasive ballet of the galactic tide, and the more abrupt, dramatic encounters of stellar perturbations. Both are crucial in dislodging these icy sentinels from their ancient, stable orbits. A comet that has been gently nudged by the persistent stretch of the galactic tide might then become exquisitely vulnerable to the sudden gravitational jolt from a passing star, a cosmic 1-2 punch that finally sends it on its long, arduous journey inwards. This intricate interplay of forces ensures that the Oort cloud is a dynamic reservoir, constantly being stirred and reshaped over the immense timescales of galactic history. And for those countless icy bodies, millions upon millions of them, that receive just the right nudge, just the right kick, their long slumber finally ends. They begin an epic, millennia-long descent, a slow, patient fall from the furthest reaches of our solar system, from the realm of the unseen and the unimaginable, towards the warmth and light of our sun. What awaits them on this long, strange journey? What stories will they tell as they finally approach the heart of our planetary system? We will explore that enchanting transformation and the glorious display of these celestial visitors in our next quiet moment together. Beyond the galactic tide and passing stars, are there other hidden forces at work, other invisible hands that reach out across the cosmic dark to stir this realm of deep slumber? Imagine, if you will, that the Oort cloud is like a vast, delicate mobile, hanging suspended in the grand, dark nursery of space. Most of the time, the tiny icy spheres on this mobile drift in serene, unchanging orbits, undisturbed in their frozen vigil. But every now and then, an invisible thread is pulled, a distant hand reaches out, and these sleepy wanderers are stirred. One of the most profound influences on the Oort cloud comes not from within our solar system, but from the immense, sprawling embrace of our very own galaxy, the Milky Way. Think of our galaxy as a colossal flat disk, a grand cosmic whirlpool of stars, gas, and dust, spinning ever so slowly. Our sun, with its surrounding Oort cloud, is just one tiny speck within this magnificent structure, nestled about 2/3 of the way out from the galactic center. As our entire solar system slowly orbits the galactic core, a subtle but persistent gravitational force acts upon the Oort cloud. This force is often called the galactic tide. Now picture the Oort cloud, not as a solid sphere, but as an incredibly diffuse, enormous cloud stretching across an unimaginable distance, so vast, in fact, that one side is significantly closer to the galactic center than the other. Just as the moon's gravity creates tides in Earth's oceans by pulling more strongly on the side of Earth closest to it, and less strongly on the far side, the immense gravity of the entire Milky Way exerts a differential pull on the Oort cloud. The part of the Oort cloud closer to the galactic center feels a slightly stronger tug than the part farther away. This isn't a violent, sudden yank, but rather a slow, relentless stretching and compressing. Imagine the Oort cloud as a giant, incredibly elastic bubble. As it moves through the varying gravitational landscape of the galaxy, through denser spiral arms and less dense regions, it is constantly being subtly elongated in one direction and squashed in another. This gentle, rhythmic stretching and squeezing, like the deep, slow breathing of the galaxy itself, can be enough to dislodge some of those icy sleepers from their stable, circular paths. It can impart just enough energy to alter their perfect equilibrium, subtly nudging them into new, more elongated orbits, or even occasionally sending them spiraling inwards towards the sun. These are truly ancient forces, having played out over billions of years, gradually sculpting and stirring the outermost reaches of our solar system, ensuring a trickle of fresh comets makes its way into the inner solar system, even from the deepest, darkest corners of the Oort Cloud. But the galactic tide isn't the only distant, unseen hand at play. Imagine our sun, with its vast entourage of planets and the even vaster Oort Cloud, as a lone ship sailing through a cosmic ocean. Most of the time, its voyage is peaceful and solitary. Yet the ocean is full of other ships, other stars, silently traversing their own paths through the galaxy. These stellar encounters, though rare in the immense emptiness of space, can have profound effects on the delicate balance of the Oort Cloud. Over the billions of years of our solar system's existence, countless stars have drifted past our sun, some closer than others. While a direct collision is extraordinarily unlikely, a close gravitational encounter can be a powerful disruptor. When another star, perhaps even a small, dim red dwarf, the most common type of star in our galaxy, often too faint to be seen with the naked eye, even if relatively close, passes within a certain range of our solar system, its immense gravitational field begins to exert a noticeable pull on the objects in the Oort Cloud. Think of it like a pebble dropped into a calm pond. The ripples spread outwards, disturbing everything in their path. Similarly, the passing star's gravity creates a gravitational ripple, a powerful unseen hand that can violently stir the icy contents of the Oort Cloud. It acts like a giant cosmic slingshot, yanking some comets clean out of their orbits and flinging them out of our solar system entirely, lost to the interstellar void forever. Others, however, are given a different kind of push, a nudge that sends them tumbling inward, embarking on incredibly long journeys towards the warmth and light of our sun, becoming what we know as long-period comets, taking thousands or even millions of years to complete a single orbit. Flow. The most powerful of these encounters can send a cascade of icy bodies towards the inner solar system, potentially triggering what scientists call comet showers. These events, though rare and occurring over spans of millions of years, remind us that even the most distant and serene parts of our cosmic neighborhood are not immune to the dynamic, ever-changing dance of the universe. The precise nature of these passing stars, their mass, speed, and distance, determines the extent of their influence. Even a star several light years away can, over vast eons, subtly contribute to the stirring of the Oort Cloud, its invisible gravitational threads reaching across the dark. And what if there's an even closer, yet still unseen gravitational influence? The possibility, though still hypothetical, is captivating. A large, undiscovered planet lurking in the farthest, coldest reaches of our own solar system, far beyond Neptune. This potential Planet 9, or Planet X, as it's sometimes called, remains a tantalizing mystery. Scientists have observed curious alignments in the orbits of some of the most distant known icy bodies within our solar system, objects even beyond the Kuiper Belt. These distant objects seem to be shepherded by an unseen gravitational force, as if pulled into a specific pattern by something massive and hidden. And if such a giant planet truly exists, its gravitational influence would extend far beyond those inner trans-Neptunian objects. It would also interact with the very innermost fringes of the Oort Cloud. Imagine a giant, invisible shepherd dog, silently patrolling the edges of the cosmic flock. Its gravitational presence would create additional perturbations, further stirring the delicate balance of the Oort Cloud, potentially sending more icy wanderers on their way towards the sun. While its existence is still being debated and sought, the idea of an unseen massive companion in our own solar system adds another layer to the intricate ballet of gravitational forces that shape the destiny of the Oort Cloud. It's a reminder that even within our own cosmic home, there are still profound secrets waiting to be unveiled, immense influences yet to be directly observed. So, whether it's the slow, steady stretch of the galactic tide, the dramatic ripple from a passing star, or the more speculative pull of a hidden giant within our own system, the Oort Cloud is far from an isolated, static entity. It is a dynamic, living part of our solar system, constantly shaped and stirred by forces both immensely distant and profoundly subtle. These influences, playing out over astronomical timescales, ensure that the Oort Cloud remains a vibrant reservoir, occasionally releasing its icy treasures to grace our night skies. But what happens to these icy treasures once they are dislodged? What is their long, solitary journey like as they begin their descent towards the inner solar system, drawn by the sun's irresistible embrace? We'll explore that next. We've spoken of this realm as if we've walked among its icy inhabitants, as if we've charted every frozen fragment. But how do we truly know of this place? How do we study a realm so vast, so dark, so incredibly far away? This brings us to the 6th chapter of our journey, a tale of observational challenges and the tireless quest of current research. Imagine, if you will, standing on a mountaintop on a moonless night, gazing across a seemingly infinite valley. Now, try to spot a single unlit pebble, no larger than a grain of rice, nestled amongst countless others, miles and miles away. This, my dear listener, is a metaphor for the profound challenge of observing the Oort Cloud. Our first great hurdle is simply the immense distance. The Oort Cloud begins perhaps 2,000 times farther from the sun than Earth is, stretching out to distances that blur the very concept of nearby. At these incredible reaches, the sun's light is so incredibly dim that any object residing there would reflect barely a whisper of illumination back towards our telescopes. It's like trying to catch the glint of a firefly's wing in a stadium-sized, darkened room from the farthest seat in the highest tier. Secondly, the objects themselves contribute to their elusiveness. The Oort Cloud is primarily composed of icy planetesimals, frozen chunks of water, methane, ammonia, and carbon dioxide. These aren't stars that glow with their own fusion, nor are they planets that reflect a significant amount of light. They are dark, silent wanderers, absorbing more light than they reflect, merging with the velvet blackness of interstellar space. They are like lumps of coal drifting through a moonless night, virtually invisible against the cosmic tapestry. Adding to this difficulty is the sheer sparsity and small size of these objects. While the Oort Cloud is vast, it is also incredibly diffuse. The individual cometary nuclei, though potentially kilometers across, are spread out over truly astronomical distances, meaning there are no bright, dense clusters for our telescopes to easily pick out. It's not a thick, opaque cloud, but rather a wispy, ethereal halo, where neighbors might be light days apart. We haven't, in fact, ever directly observed an Oort Cloud object in its native habitat. All our understanding is built upon clever detective work, indirect evidence, and brilliant inference. So, how do scientists, with their curious minds and powerful instruments, begin to unravel the secrets of this phantom realm? They turn to our messengers from the deep, the long-period comets. These celestial snowballs with their magnificent tails are like postcards from the Oort Cloud, delivering precious clues right to our inner solar system doorstep. When a passing star or the galactic tide subtly nudges an Oort Cloud object out of its distant lazy orbit, it can begin a slow, decades-long plunge towards the sun. By carefully studying the extreme elliptical orbits of these comets, their paths that sweep in from vast distances and take thousands or even millions of years to complete a single journey around the sun, astronomers can retroactively trace their origins. The physics of their paths tells us they must have come from a spherical reservoir far beyond the planets. And by analyzing the chemical composition of their glowing comas and tails, scientists gain insights into the primordial materials that formed the Oort Cloud, offering glimpses into the very earliest days of our solar system, preserved in deep freeze. But the hunt for direct residence continues. Scientists are pushing the boundaries of detection with extraordinary patience. One exciting avenue involves the study of extreme trans-Neptunian objects, ETNOs. These are objects like Sedna, or 2012 VP-113, discovered lurking in the outer reaches of the Kuiper Belt and beyond. While not strictly Oort Cloud objects, their highly elongated orbits and distant closest approaches to the Sun suggest they might be inner Oort Cloud members, or, at the very least, objects whose formation and evolution are intimately tied to the processes that shaped the Oort Cloud. They are like stepping stones, leading us closer to the true outer frontier. Their unusual orbits also spark another intriguing area of research: the potential gravitational influence of an unseen giant planet, often dubbed Planet 9. If such a world exists, its gravitational tug could be responsible for sculpting the orbits of these ETNOs and perhaps even influencing the very dynamics of the inner Oort Cloud, acting as an invisible shepherd. Looking to the future, new observational behemoths are being brought to bear on this cosmic mystery. The Montevera C. Rubin Observatory, currently under construction, promises to revolutionize our search. With its incredibly wide field of view and remarkable light-gathering power, it will systematically survey the entire southern sky, capturing images of unprecedented depth. Imagine a cosmic sweep, meticulously charting millions of distant, faint objects. While discovering true Oort Cloud residents might still be a long shot, it vastly increases our chances of finding more ETNOs, extending our understanding of the solar system's farthest known inhabitants and pushing our observational limits closer to the Oort Cloud's inner edge. Beyond direct imaging, scientists are exploring innovative techniques like gravitational microlensing. This phenomenon occurs when a massive, unseen object passes in front of a much more distant background star, briefly magnifying the star's light. While incredibly challenging to apply to individual Oort Cloud objects due to their small size and the vast distances, it offers a theoretical possibility of detecting truly dark, isolated bodies in the far reaches of space, objects that would otherwise remain utterly invisible. Finally, the silent architects of knowledge, computer simulations, play an invaluable role. by inputting our best understanding of stellar dynamics, planetary formation, and the gravitational ballet of the galaxy. Scientists can create complex models that simulate the formation and evolution of the Oort Cloud over billions of years. These digital universes allow researchers to test different hypotheses, exploring how the Oort Cloud might have been populated, how many objects it might contain, and how it has been subtly shaped by passing stars and the immense gravitational forces of the Milky Way. The Oort Cloud, then, remains one of the most enigmatic and least understood structures in our solar system. It's a cosmic ghost whose presence we infer from the echoes of its icy inhabitants and the subtle gravitational whispers it sends our way. Yet, the relentless curiosity of humanity, armed with ever more powerful tools and ingenious methods, continues to chip away at its secrets, slowly illuminating the darkness at the edge of our home. It's a testament to the fact that even the most distant and elusive mysteries can, with time and ingenuity, begin to yield their truths. But as we've learned how we observe this distant realm, a profound question naturally arises. How did this magnificent icy sphere come to be? What grand cosmic events were responsible for scattering these icy building blocks so far from the sun, forming a silent sentinel at the very edge of our solar system? Join me next as we explore the fascinating theories of the Oort Cloud's mysterious origins. Understanding how we observe the Oort Cloud is one thing, but understanding why it matters, what role it has played in shaping everything we know, is quite another. For this distant realm, though seemingly inert, holds a profound secret about the very genesis and evolution of our solar system. Imagine, if you will, the early days of our cosmic neighborhood, a time of swirling dust and gas coalescing into the sun and its nascent planets. It was a period of immense chaos and creation, a cosmic construction site where the foundations of everything we know were being laid. And it is from this tumultuous birth that the Oort Cloud derives its most crucial role. Picture our young solar system, perhaps 4.6 billion years ago. The sun had just ignited, and around it a vast flat disk of gas and dust, known as the protoplanetary disk, swirled like an enormous cosmic eddy. Within this disk, tiny particles began to collide and stick together, gradually growing into pebbles, then rocks, then planetesimals, the building blocks of planets. Close to the sun, where it was warmer, rocky planets like Earth and Mars began to form. But further out, in the colder, more distant realms, icy bodies dominated. These were the origins of what would become the gas and ice giants, Jupiter, Saturn, Uranus, and Neptune. Now, here's where the Oort Cloud truly begins to take shape. As these massive gas and ice giants grew, their immense gravitational fields began to exert a powerful influence on their surroundings. They were like cosmic shepherds, rounding up material, but also like celestial pinball machines, scattering vast quantities of icy debris. Imagine a child's marble game, but instead of small marbles, we have countless icy planetesimals. And instead of a hand, we have the crushing gravity of Jupiter and Saturn. These colossal planets, particularly in their early, more dynamic stages, flung billions upon billions of these icy fragments outwards, sending them hurtling on trajectories that would eventually lead them far, far away from the sun. These icy exiles didn't just vanish into the void. Instead, their paths were stretched and distorted by the gravitational pull of the nascent giant planets, until many of them found themselves in extremely elongated orbits, some so vast that they would take millions of years to complete just one circuit around the Sun. They were nudged, perturbed, and eventually settled into the distant spherical shell we now call the Oort Cloud. It's like the attic of our solar system, filled with forgotten treasures from its youth, packed away and left largely undisturbed for eons. This process wasn't a gentle dispersal. It was a violent expulsion, a clearing out of the primordial disk, essential for the inner solar system to stabilize and for life to eventually emerge. Without this scattering, much of that icy material might have remained closer in, posing a constant threat of bombardment to the forming inner planets. One of the most profound roles of the Oort Cloud in solar system evolution is its function as a pristine time capsule. These icy inhabitants, born from the very same material that formed our sun and planets, have been preserved in a deep freeze, almost untouched by the radiation and solar wind that constantly bombards objects closer to the sun. They reside in a realm where temperatures plunge to near absolute zero, and the solar light is but a faint glimmer, barely distinguishing them from the interstellar darkness. This extreme distance and cold has meant that their chemical composition has remained virtually unchanged since the solar system's earliest moments. When we study comets that originate from the Oort Cloud, we are essentially looking at samples of the original building blocks of our solar system, remnants from a time before the planets fully formed and differentiated. It's like finding a perfectly preserved fossil from billions of years ago, offering us direct clues about the conditions and ingredients present at the very dawn of our cosmic home. They whisper secrets about the types of molecules, the ratios of isotopes, and the physical processes that were active in that ancient swirling disk. But the Oort Cloud is not entirely static. It's also a dynamic reservoir, playing a crucial ongoing role in the solar system's evolution by acting as the primary source of what we call long-period comets. Every so often, something from beyond the solar system, perhaps a passing star, or even the subtle gravitational tug of the Milky Way galaxy's spiral arms and giant molecular clouds as our sun orbits the galactic center, will give one of these slumbering icy bodies a gentle gravitational nudge. This nudge, though seemingly insignificant from such vast distances, is enough to alter its incredibly delicate, elongated orbit. Imagine a tiny, icy pebble millions of kilometers away, suddenly feeling a faint, irresistible tug. This pull causes it to begin a long, slow fall towards the inner solar system, an epic journey that can take thousands or even millions of years. As it approaches the sun, the warmth causes its ice to sublime directly into gas, carrying dust particles with it, forming the magnificent coma and tail that characterize a comet. These long-period comets are not just beautiful celestial visitors. They are messengers from the past, carrying those ancient, pristine materials into our modern era. They deliver fresh insights into the composition of the early solar nebula, sometimes even bringing organic molecules and water that could have played a role in seeding early Earth with the ingredients for life. The Oort Cloud, then, is not just a storage locker. It's a cosmic delivery service, periodically refreshing our understanding of our own beginnings. Furthermore, The very existence and characteristics of the Oort cloud provide invaluable clues about the early turbulent dynamics of the giant planets themselves. Theories of solar system formation, like the NICE model, propose that Jupiter, Saturn, Uranus, and Neptune didn't always reside in their current, relatively stable orbits. Instead, they may have undergone a period of significant migration, shuffling their positions dramatically early in the solar system's history. This planetary ballet, with its gravitational pushes and pulls, would have been the primary sculptor of the Oort cloud, shaping its overall size, density, and the distribution of its icy inhabitants. The scattered objects that ended up in the Oort cloud are essentially fossilized records of these early gravitational interactions. By studying the orbits and compositions of Oort cloud comets, scientists can work backward, like cosmic detectives, to reconstruct the pathways and gravitational forces that shaped the outermost reaches of our planetary system, gaining a deeper understanding of how our giant planets arrived at their current configurations. The Oort cloud's properties are a crucial testbed for these grand theories of planet migration, providing observational evidence that helps confirm or refine our understanding of this chaotic, yet ultimately stabilizing phase of solar system evolution. So, while the Oort cloud remains largely unseen, a vast, dark, and silent realm on the very fringes of our celestial neighborhood, its role in the story of our solar system is undeniable and profound. It is the repository of our deepest past, the occasional bringer of ancient materials, and a silent witness to the epic forces that sculpted our cosmic home. Its secrets are still being slowly unraveled, each cometary visitor a new page in a history book written in ice and starlight. As we gently drift through these vast, cold reaches, perhaps we can contemplate the enduring mysteries held within the Oort cloud, and how even the most distant and seemingly insignificant parts of our universe play a vital role in the grand, unfolding narrative of cosmic evolution. But what about another celestial belt, much closer to home, yet still far beyond the familiar planets? What other icy relics might it hold? We'll explore that next. We've traced the Oort cloud's origins, its structure, its role in our solar system's story, but this knowledge comes from afar, from inference and calculation. A question naturally arises: might we one day journey there ourselves? Might humanity ever touch these ancient frozen shores? But humanity, with its insatiable curiosity, rarely allows a mystery to remain untouched forever. Even as you prepare for your own journey into slumber, scientists and engineers around the world are dreaming of tomorrow's voyages, charting courses for missions that might one day sail to the Oort cloud itself. Imagine, if you will, the challenge. Our most distant emissaries, the Voyager probes, have traveled for decades, pushing beyond the heliopause, the sun's magnetic bubble. Yet, even they are still just dipping their toes into the inner fringes of the Oort cloud, if that. To truly reach its heart, to explore its vast icy depths where countless cometary nuclei reside, would require a leap in technology, a new kind of starship for our own stellar neighborhood. The journey isn't just measured in light years, but in generations, in the very fabric of time itself. The chemical rockets we've used to launch our explorers to the moon and even to distant planets are like powerful but brief fireworks. They burn intensely for a short time and then coast. For a voyage to the Oort cloud, we need something different. A gentle, persistent push, or a truly revolutionary surge of power that can sustain itself for decades or even a century. Think of it like a marathon, not a sprint. One of the most promising ideas already seeing use in our solar system is bar-ion propulsion. Instead of burning fuel, these engines use electricity to accelerate charged atoms, or ions, out the back of the spacecraft. It's a whisper-soft thrust, far less dramatic than a rocket launch, but it's incredibly efficient and can accelerate a spacecraft to much higher speeds over time. Imagine a tiny, steady breeze pushing a delicate leaf, gathering momentum with every passing moment. Missions like NASA's Dawn spacecraft, which explored Vesta and Ceres, used ion thrusters to subtly reshape their orbits over years. While magnificent for inner solar system exploration, even advanced ion thrusters would take many, many decades, perhaps even centuries, to reach the bulk of the Oort Cloud. We need to go faster to find a way to make that gentle breeze into a sustained gale. Another elegant concept borrows directly from the sea: solar sails. Instead of propulsion from an engine, these spacecraft unfurl vast, mirror-like sheets, often made of incredibly thin, reflective material. They don't catch the wind in the way a sailboat does, but rather are propelled by the infinitesimal push of sunlight itself, photons, those tiny packets of light gently bouncing off the sail's surface. It's a very subtle force, like a feather drifting on an invisible current, but in the vacuum of space, over vast distances, this constant pressure can accelerate a spacecraft to astonishing velocities far beyond what chemical rockets can achieve. Imagine a cosmic kite catching the faint glimmers of our sun's light and being pushed ever outward, gaining speed with each solar breath. Projects like LightSail 2 have already demonstrated the feasibility of this elegant dance with starlight in Earth orbit. The challenge for Oort Cloud missions, however, is that as you travel further from the sunlight grows weaker, diminishing the wind that powers your sail. Future solar sails might need to be truly immense, perhaps kilometers across, or even use powerful lasers from Earth to push them, a concept explored by initiatives like Breakthrough Starshot, which envisions tiny probes propelled to other star systems in mere decades. To truly slash those centuries-long travel times to the Oort Cloud, we might need to harness the very power of the atom. Nuclear propulsion comes in various forms. Nuclear thermal propulsion, NTP, uses the heat from a nuclear reactor to superheat a propellant, like hydrogen, expelling it at high velocity. This is a much more powerful and efficient thrust than chemical rockets. Think of it as a controlled miniature star powering an engine, providing a steady, robust push that could shorten journeys to the Oort Cloud from many centuries to perhaps a few decades. Then there's nuclear electric propulsion, NEP, where a nuclear reactor generates electricity to power advanced ion thrusters, combining the best of both worlds, the immense power source of nuclear fission with the high efficiency of ion thrust. These are not dreams of science fiction, but technologies actively being studied and developed by space agencies, seen as crucial stepping stones for human missions to Mars and beyond. And for the truly distant future, where the Oort Cloud becomes just another stop on a grander interstellar journey, scientists envision fusion propulsion. This is the same process that powers our sun, where light atomic nuclei combine to release vast amounts of energy, If we could safely and efficiently control fusion reactions in a spacecraft, we would have an engine of unparalleled power and endurance. Imagine creating a tiny, contained sun on board your vessel, providing a continuous, powerful thrust that could propel a probe to the outer Oort Cloud in perhaps just a couple of decades. Projects like the historic Project Daedalus in the 1970s and its modern successor, Project Icarus, studied such concepts, designing hypothetical interstellar probes that would use fusion rockets for rapid transit. These are truly star-born engines, carrying a piece of the sun's power with them into the deep cosmic night. Beyond even fusion, the realm of pure theoretical physics beckons with concepts like antimatter propulsion, where matter and antimatter annihilate each other, converting their entire mass into energy, the most efficient reaction possible. Or even the truly mind-bending idea of warp drives, theorized by physicists like Miguel Alcubierre, which would subtly bend space-time around the spacecraft, allowing it to travel faster than light, relative to distant observers, without actually exceeding the speed of light locally. These are the distant echoes of tomorrow's dreams, perhaps centuries away, but they illustrate the boundless ambition of our quest to understand the universe. But propulsion is only one piece of this cosmic puzzle. Any mission to the Oort Cloud would also need to be incredibly resilient. It would require some autonomous systems, intelligent software that could make decisions and react to unexpected events without constant human intervention. The communication delay would be immense. Light takes hours, days, even months to cross such distances, making real-time control impossible. So, these probes would need to be pioneers in their own right, capable of navigating, observing, and even self-repairing in the profound isolation of deep space. They would also need innovative power sources, far beyond what solar panels could provide so far from the sun advanced. Radioisotope thermoelectric generators, RTGs, which generate electricity from the decay of radioactive isotopes, or even small compact fission reactors, would be essential to keep the lights on and the instruments running for decades. Imagine a tiny, resilient heart beating steadily in the cold vacuum, providing warmth and energy to the scientific instruments for an almost eternal journey. What would these daring missions seek? They would be time machines, searching for the raw, untainted material from which our solar system was born, preserved in the deep freeze of space. They might discover new dwarf planets or even rogue planets captured by our sun's distant gravity. They would map the true extent of our solar system, charting its final boundary before the ultimate emptiness of interstellar space. They would be our eyes and ears at the very beginning of everything, gathering clues about the grand cosmic story that began billions of years ago. This grand journey, this ambitious dream of reaching the Oort Cloud, reminds us that even as we rest, the universe continues its silent, majestic dance, holding countless secrets. And perhaps, one day, as we continue to dream and to build, our tiny probes will finally sail into those distant, icy realms, carrying with them the hopes and curiosity of all humanity. What wonders might they truly behold when they finally arrive at the outer limits of our sun's embrace? But before we ponder those distant discoveries, let us gently turn our attention to the treasures that may already be closer than we think, the familiar visitors that come to us from this very distant cloud, the comets themselves. We've spoken of visiting the Oort Cloud as explorers, as scientists seeking knowledge, but what if we went as something more? As settlers, as seekers of resources? For a long time, we viewed this region purely as the primordial wellspring of comets, a frozen archive of the early solar system. But in the quiet whispers of scientific inquiry, a new thought has begun to shimmer, a potential that transforms this distant realm from a mere celestial attic into a cosmic deep freeze, brimming with the very elements that could fuel humanity's grandest expansion. Imagine, if you will, these countless icy moats, each a small, silent vault, holding within its frozen heart not just water ice, but also frozen ammonia, methane, carbon dioxide, and carbon monoxide. These are not merely inert chunks of ice. They are chemical storehouses, each one a tiny, complex nebula of the very elements that form the building blocks of life and civilization. Beneath their icy veneers, some might even contain a scattering of silicates and rocky materials, remnants from the nascent solar system's dust and grit. These are the volatiles, the lightweight, easily vaporized compounds that are so precious and often finite on planetary surfaces. Yet here, they exist in quantities that beggar belief, dispersed across an astronomical canvas. Now, why might humanity, nestled comfortably on its vibrant blue marble, ever cast its gaze so far into the profound chill of space? The answer lies in the enduring dream of growth, the persistent thrum of curiosity, and the simple, undeniable fact of finite resources. Our Earth, though bountiful, is not limitless. As our global population grows, as our technological ambitions soar, the demand for water, for energy, for raw materials of every kind steadily increases. The Oort Cloud, in this light, transforms from a distant curiosity into a potential salvation, a future reservoir of critical resources, waiting patiently in the dark. Chief among these treasures is water ice. On Earth, water is life, and in space, it's even more. It's not just for drinking and sustaining biological processes. Water is the ultimate Swiss Army knife of space resources. Through electrolysis, it can be split into hydrogen and oxygen. Hydrogen, when supercooled, becomes liquid hydrogen, an incredibly potent rocket fuel. Oxygen is not only breathable air, essential for life support in future space habitats, but also a crucial oxidizer for those very same rocket engines. Thus, an Oort Cloud object, rich in water ice, is not just a chunk of frozen water, it's a potential celestial gas station, a life support system, and a foundational element for manufacturing in the void, all rolled into one distant package. These icy bodies, though small individually, collectively represent a staggering quantity of water, more perhaps than all the oceans of Earth combined. And beyond water, the other volatiles like methane and ammonia offer a diverse toolkit for future spacefarers. Methane, too, can serve as a rocket fuel, offering an alternative to hydrogen. Ammonia, rich in nitrogen, is vital for fertilizers in closed-loop agricultural systems within space habitats and can be used in various industrial processes. Carbon dioxide and carbon monoxide, while often associated with waste products, are fundamental sources of carbon and oxygen for manufacturing plastics, advanced materials, and even for creating synthetic atmospheres. Imagine humanity, not just mining for minerals, but for the very breath it takes, for the fuel that propels its ships, for the very materials it builds its new homes with, all sourced from these ancient, icy wanderers. And this grand vision, however, is not without its monumental challenges. The distances involved are truly staggering. To reach the inner edge of the Oort Cloud, approximately 2,000 astronomical units from the Sun, would require propulsion technologies far beyond our current capabilities. Even with theoretical fusion rockets or advanced laser sails, travel times would still be measured in decades, not months. The journey itself would be a multi-generational endeavor, a testament to long-term planning and unwavering commitment. Moreover, detecting and tracking these small, dark objects in the profound blackness is an immense task. They are faint, fleeting, and spread incredibly thin, like grains of sand scattered across an entire desert. This means developing highly sensitive, long-range detection systems, perhaps even deploying a network of probes specifically designed to map this outermost frontier. Once reached, the extraction and processing of these resources present their own unique hurdles. The extreme cold, just a few degrees above absolute zero, would require specialized robotics and engineering solutions capable of operating in such unforgiving conditions. Low-gravity environments would necessitate anchoring systems and innovative mining techniques, perhaps involving directed energy or gentle ablation rather than traditional digging. The concept of in situ resource utilization, SRU, where local materials are used to create what's needed, would be paramount. Instead of hauling everything from Earth, future spacefarers would become adept at living off the land, transforming ice into fuel, gases into building blocks, right there among the icy moats. Cloud. This kind of expansion isn't just about resource acquisition. It's about the very survival and flourishing of our species. By tapping into the Oort Cloud, humanity would be taking a monumental step towards becoming a truly multi-system civilization, less vulnerable to catastrophic events on any single planet. It represents a shift from being a terrestrial species to a cosmic one, not just exploring but inhabiting the vastness beyond. It is an undertaking that would redefine our place in the universe, transforming us from observers into active participants in the grand cosmic tapestry, building new outposts, creating new economies, and fostering new cultures among the stars. The Oort Cloud, then, is more than just a distant collection of frozen rubble. It is a profound testament to the potential for future innovation, a silent promise of endless possibilities. It embodies the ultimate frontier for resource acquisition and human expansion, a place where our most audacious dreams of colonizing the cosmos might one day take root. And as we consider the silent, icy masses that dwell so far from our sunny home, we begin to wonder not just what they hold, but what they might allow us to become. Perhaps, as our eyes grow accustomed to the deep darkness, we might begin to discern the faint outlines of the next great chapter in humanity's story, an odyssey that begins with the very objects that guard the edge of our solar system. But how exactly might we begin to harness the power of such distant dark matter? But whether humanity reaches the Oort Cloud or not, its story will continue, stretching far beyond our own lifetimes, far beyond even our species' tenure on Earth. For even in its majestic solitude, this icy realm is not truly static. It's a living, breathing tapestry of cosmic forces, constantly, gently, being reshaped by the grand ballet of the cosmos. Imagine, if you will, a vast spherical ocean of ice and dust, incredibly distant, yet eternally touched by unseen currents and whispers from beyond. The first whisper comes from its celestial neighbors, other stars undertaking their own vast journeys through our galaxy. Our sun is just one of hundreds of billions of stars in the Milky Way. And while the space between them is immense, it is not truly empty. Every now and then, over eons, another star, perhaps 1,000 or even 10,000 times more massive than our Earth, drifts close enough to the sun's gravitational domain to make its presence felt in the distant Oort Cloud. It's not a violent collision, no. Think of it more as a gentle yet profound gravitational nudge, like a silent ship passing far off in the night, its wake subtly stirring the waters of our cosmic reservoir. These gravitational ripples can disturb the delicate, ancient orbits of the icy bodies within the Oort Cloud. A tiny pebble, a snowball the size of a mountain, even a dwarf planet. Each might feel this imperceptible tug, shifting its trajectory ever so slightly. For some, this nudge might be just enough to propel them outward, forever casting them adrift into the vast, cold emptiness between the stars, becoming interstellar wanderers, lost to our solar system's embrace. For others, however, the nudge might send them on an entirely different path, inwards, towards the warmth and light of our sun, beginning a journey that could span hundreds of thousands, even millions of years. But the Oort Cloud is also subject to an even grander, more constant force, the gravitational embrace of the entire Milky Way galaxy itself. Our sun, with its attendant Oort Cloud, orbits the galactic center, a journey that takes hundreds of millions of years to complete. As we revolve, the combined gravity of billions of stars, vast nebulae, and dark matter within the galaxy exerts a subtle but persistent tidal force on our solar system. Imagine our solar system as a single, delicate drop of water within an unimaginably vast cosmic ocean. This ocean, the Milky Way, continuously stretches and pulls at our drop. This galactic tide doesn't create a violent surge, but rather a slow, continuous stretching motion across the immense expanse of the Oort Cloud. It's like a gentle, unseen hand, constantly kneading and shaping the farthest reaches of our sun's gravitational dominion. This tidal force preferentially dislodges objects at the poles of the Oort Cloud, which are perpendicular to the galactic plane, and also at the equator, parallel to the galactic plane, subtly guiding some of these icy wanderers inwards, initiating their long, slow descent towards the inner solar system. These two forces, the occasional close encounters with passing stars and the ceaseless subtle tug of the galactic tide, are the primary architects of the Oort Cloud's long-term evolution. And what becomes of these objects once they are gently nudged or stretched from their ancient slumber? For those few, relatively speaking, that are sent inwards, a new chapter begins. They embark on an epic journey that might last for hundreds of thousands or even millions of years, slowly falling towards the sun, These are the fabled long-period comets, the celestial messengers from the deepest, coldest reaches of our solar system. They arrive from seemingly nowhere, often without warning, appearing as fuzzy patches of light in our night sky, growing brighter as they approach. As they get closer to the sun, its gentle warmth begins to awaken them. The ice, preserved for billions of years, starts to sublimate, turning directly from solid to gas, creating the ethereal coma and the magnificent tail that stretches for millions of miles, shimmering in the sunlight. Each long-period comet is a fleeting glimpse into the primordial past, a testament to the Oort Cloud's enduring role as a cosmic reservoir. After their dramatic flyby, if they survive the sun's intense heat and radiation without completely disintegrating, these comets will often swing back out into the deep space, though usually on new, altered orbits. Some might return in tens of thousands of years. Others might be ejected entirely, having gained enough energy from the sun's gravity to escape its grasp forever. But what of those objects that are ejected outwards, away from the sun, past the very edge of our solar system? They become true interstellar nomads, forever severed from their cosmic birthplace. They might drift through the vastness of space for billions of years, perhaps eventually being captured by another star system, or perhaps never finding a new home, simply wandering the cosmic voids until the end of time. This outflow of cometary material means that the Oort Cloud is not an inexhaustible supply. Over the immense timescales of cosmic history, it is slowly, steadily being depleted. Each passing star, each turn around the galaxy, each long-period comet that either falls into the sun or is flung out into interstellar space subtracts a tiny piece from this grand icy sphere. It's a process akin to grains of sand slowly slipping through an hourglass, marking the passage of unimaginable eons. While the Oort Cloud is vast beyond comprehension, containing trillions of icy bodies, these forces of erosion are constant. Scientists estimate that over the age of the solar system, billions of years, a significant fraction of its original population has already been lost. It's a slow cosmic erosion, a testament to the impermanence of even the most ancient and distant structures in the universe. And what will be the ultimate fate of this magnificent distant cloud? Its destiny is inextricably linked to the fate of our own star, the Sun. Billions of years from now, our Sun, like all stars, will begin to evolve, reaching the twilight of its life. First, it will swell into a red giant, expanding dramatically. Its outer layers will balloon outwards, perhaps even encompassing the orbits of Mercury, Venus, and possibly even Earth. During this phase, the Sun will become much more luminous and release a much stronger solar wind, a powerful outflow of particles. While the Oort Cloud is far, far too distant to be engulfed by the red giant Sun, this increased solar wind and luminosity might have subtle effects on the very outermost fringes of the cloud, perhaps subtly influencing the most loosely bound icy bodies, or stripping away some of the thinnest icy layers of objects within it. But then, after its red giant phase, our Sun will eventually shed its outer layers, forming a beautiful planetary nebula, and its core will contract into a tiny, incredibly dense white dwarf star. This white dwarf will be a mere remnant of our once glorious Sun, a faint, cooling ember in the vast darkness. At this point, the Oort Cloud will still exist, a ghostly shell of icy remnants orbiting a practically invisible star. It will be a silent, frigid graveyard, illuminated only by the distant glimmers of other stars, its icy inhabitants locked in eternal, unchanging orbits around a dead sun. The forces of galactic tides and passing stars will still continue their gentle work, but the overall population will have dwindled significantly. So, the Oort Cloud, though seeming so permanent and still, is a dynamic entity, slowly but surely evolving, giving birth to comets and scattering its children to the interstellar winds. It's a grand story of cosmic persistence and transformation, played out over timescales that humble our human understanding. From its violent birth in the chaos of planetary formation, through its current role as a cosmic reservoir, to its eventual fate orbiting a dying star, the Oort Cloud story spans the entire lifetime of our solar system, a silent witness to everything that was and everything that will be. And so, as our exploration draws to a close, let's bring with us the serene image of the Oort Cloud, softly nestled in the cosmic dark. Imagine it now, not as a place of stark emptiness, but as a vast ethereal shell, a whisper of cosmic dust and ice, cradling our familiar world within its immense, silent embrace. It has been a long voyage, not just for us tonight, but for those countless icy fragments that form this distant realm. They once knew a brighter, hotter home, a bustling nursery closer to the young sun, where planets were still finding their footing, and light danced with a fiery enthusiasm. But time, in its gentle, relentless flow, carried them outward, not in a tumultuous rush, but in a slow, almost dreaming drift. Like tiny, slumbering seeds, they were nudged and guided far, far away, until they found their quiet sanctuary, thousands of times further than Earth's sunlit path. This was their journey, a gentle scattering, a soft migration, settling into a vast, spherical memory of our solar system's beginnings. They didn't race, they simply expanded, slowly, patiently, until they formed this grand, silent sphere that now enfolds us all in its peaceful mystery. Think of the Oort Cloud as an ancient, patient guardian. It doesn't roar or shine brightly. It simply exists, a quiet testament to the slow, beautiful ballet of creation. Within its immense sphere, billions upon billions of icy bodies drift, each one a tiny, frozen echo of the moment our sun first flickered into being. They hold within them the very breath of primordial gas and dust, unchanged for eons, undisturbed by the hurried pace of the inner planets. They are the keepers of deep time, the silent witnesses to the universe's grand, unhurried unfolding. Their journey wasn't about destination in the way we usually think. It was about finding a state of enduring peace, a quiet orbit that holds them in a timeless embrace. And from this vast, tranquil reservoir, every so often, one of these slumbering wanderers awakens. A gentle nudge from a passing star, a subtle ripple in the fabric of space, and one of these icy fragments begins its own long, slow descent towards the warmth of the sun. It's not a violent departure, but a graceful awakening, a slow, majestic fall that eventually brings a comet, a fleeting visitor, to grace our night skies. These are the messengers, the dream weavers, bringing whispers from the very edges of our cosmic home, carrying stories from the quiet, ancient heart of the Oort Cloud. So, as we prepare to drift into our own slumber, let the image of the Oort Cloud settle softly in your mind. Its immense distance is not a separation, but a comforting encompassment. Its quietude is not an emptiness, but a deep, resonant peace. It reminds us that even at the furthest reaches, there is a gentle order, a patient waiting, a silent journey that continues without haste or worry. There is a profound comfort in realizing that our entire solar system, with all its bustling planets and vibrant life, is held within this vast, tranquil shell of ice and dust, much like a precious pearl within an enormous, softly glowing oyster. Let the thought of those tiny icy worlds drifting in their eternal serene ballet inspire a deep calm within you. Their long journey, from the sun's fiery birth to their present distant repose, mirrors the quiet, continuous journey of life itself, a slow, beautiful unfolding, finding its own gentle rhythm and its own peaceful place. The Oort Cloud is a reminder that even in the vastness, there is a gentle holding, a soft presence that assures us of the universe's enduring tenderness. Now, as your own journey tonight leads you into the soft embrace of sleep, carry with you this sense of vast, quiet peace. Imagine yourself drifting gently, like those ancient icy bodies, through the calm, dark ocean of space. Let your thoughts be light, your breath be soft, and your heart be still. The Oort Cloud continues its silent, majestic dance, even as you close your eyes, protecting and encompassing our vibrant home. And just like those distant, quiet travelers, your own dreams can now begin their gentle, peaceful journey, carrying you softly into the boundless wonders of the night. Sleep tight, knowing the universe holds you gently always. Good night.